All right, so today we're talking about thermal strain. We talked about thermal stuff yesterday. We talked about strain last week. So we are going to be putting them together. So first thing let's talk about is what is thermal strain? It's just a fancy type of strain, right? And you are correct. So that means that thermal strain is just going to be a different strain. So strain is equal to your delta L over L. Ta-da! But where this gets more interesting is if you think about it, combine it with material. Let's pretend that we've got a bar of iron. All right, so here's our metal. We're going to fix it to the wall here. So this wall is going to be stationary. It's not going to move. And here's the bar. It's cold, and we are going to heat it up. When we heat it up, it's going to expand, as we figured out yesterday. We know how to calculate all that. We can calculate that because your delta L is going to equal alpha L delta T. And we could look it up for any material that we felt like. Now, right now, the metal expanded. Now, this means that there's no stress on there and there is no strain. For this guy, strain is equal to 0. But it has a delta L, right? I mean, this is a change in length. Well, yes, it changed in length, but it wants to be that length, all right? So this delta L is for thermal expansion, okay? But it's not the same as this delta L here. Now, okay, so I get what you're saying here. All right, all right. So now what we're going to do is we're going to have another bar over here. Let's give a counter example here. This bar is going to be between two walls. All right, so here's the cold version. Cold version goes across. It fits exactly in there. Beautiful. Okay, now we heat it up. We're going to make it hotter. What's going to happen is it's going to stay the same size. All right, it's going to stay the same size because it's wedged in between the two walls. So there's no delta L for expansion here, but it would want to expand this much. But it's being compressed by the walls, so it can't do that. So this is going to be a delta L, and this is going to be for the strain. So it is going to have strain on this one. So we'll say strain is greater than 0 because it wants to be bigger, like the first pairing was, but it can't. So there's a change in length that's compressing it. So there's a compression strain involved in this. And if you know how much that delta L is, it's going to be equal to this delta L. So these two are the same for this situation because we're saying they're the same temperature. All right, so let's do a practice problem. We've got a steel bar between two rigid walls heated from 15 to 80. What is the strain? So if we heat it up, it's going to want to expand, but it's not going to be able to. There's going to be a force pressing it back. We're going to worry about stress later on, but we're just going to do strain today. So first thing we got to figure out is how much it wants to expand by. So our delta L is going to equal alpha L delta T. Well, we know what alpha is. Here's your graph or chart over here. This is steel. So we got 17. Remember, it's 17 times 10 to the minus 6. So that's that. Our L is 2, and the change in temperature, 15 to 80, is going to be going up by 65 degrees. Okay, so that means our delta L is going to be 0.00221 meters. Sounds good, sounds good. Now the only problem is the walls aren't going to budge. So they are going to be actually squeezing it together by 0.00221 meters. To figure out the strain, we're going to use him. We have delta L over L. we know what the delta L is because they're being compressed by 0.00221. And the original length is going to be 2, but the original length is 2.00221, because if it didn't have any stress, that's how long it would be. But the change in length is going to be there. Now, this is very small compared to this. It's not really going to change very much. Okay, so usually you can just leave it off, but for exactness sake, we can leave it on there. So once we do that, we are going to divide the two numbers, and we are going to get 0.001104, we'll say. I'll just leave it like there. Hey, so that is the stress. Now, if you remember back in the day, that is a small number. There is no unit. So sometimes we kick it over to micro. So 1, 2, 3, 4, 5, 6. So this is going to be 1104. There we go. Okay, either one is fine here. All right, let's keep going with the next one. Here's another one, same kind of situation. See if you can figure it out. Pause the video. Good job. Maybe. We'll find out. So we have a window. It's 1.5 meters tall. This time it's cooling. All right. Now, even though it's cooling, it would work the same way. Okay. So it's being pulled upward by the frame here. Since it's attached to the frame, it wants to be down here. It's pulled up. So our delta L is going to equal our alpha L delta T. For glass, we have 9. 9 times 10 to the minus 6 times 1.5 times delta T is 115 here. Okay, so our delta L is going to equal 0.00155 meters. Now what we're going to do is plug that into our stress formula here. So our stress is going to equal, strain is going to equal delta L over L. Okay, so our delta L is 0.00155. There we go. And our L, our original length, is going to be this guy here. So that means that we are going to have to subtract 1.5 minus 0.0015. So we are going to put as the denominator 1.4985. All right, because here's our delta L and here's our L. All right, so once we divide those guys, we are going to get 0.001034. 2, 1, 2, 3, 4, 5, 6, or 1034 micro. Nice. Hey, and that is it. So we are going to merge this with stress later on, but hopefully you're feeling all right with strain. Go get 'em.